So today's presentation is by Paola. So Paola is a final year PhD student at Northumbria University. She completed her BSc in physics and astrophysics also at Northumbria University and completed her master's in theoretical physics at the University of Edinburgh. Paola's research focuses on the ionospheres of the giant planets. And today's title of Paola's talk, as we can see on the screen, is JWST discovers the vertical structures of Uranus's ionospheres. You can take it away, Paola.
Thank you. Thank you very much. Yes, today I'll present to you some results on Uranus ionosphere with JWST observations. So, first of all, well, it's not working. First of all, it's not working. Okay, the Uranus environment. So Uranus is a very special and peculiar planet. It's one of the ice giants, so its mass and its radius, it's quite bigger than Earth's. But also that's not the only peculiar thing about this planet. In fact, its axial tilt is quite extreme. It's almost at 98 degrees. And so this has strong implication on seasonal variation. But also the magnetic field is rather peculiar because it's not only weak, but it has a large tilt too, which means that its center is offset. And this results in a very unique magnetospheric geometry, which then creates complex auroral morphologies. Here we can see the magnetosphere of Uranus whilst the planet rotates, and we can see the flip of the magnetic field and all the magnetic field lines going all over the place, really. So very, very extreme, a very extreme environment. So as I mentioned, my talk focuses on the ionosphere. So the ionosphere is this interface region between the space environment above and the atmosphere below. The ionosphere can be produced either with incoming solar EUV photons or energetic particles, for example, from auroral phenomena. The ionosphere presents an excited part, let's say, which we can observe in the ultraviolet, for example, with the Hubble Space Telescope, or another phenomena such as ionization creates ions such as H2+, which then reacts with charged particles and electrons in the ionosphere and creates H3+, another ion in the ionosphere. Now we can use H3+ observations and the spectrum that we can see from this emission to probe the properties of the ionosphere. So from the spectrum, we can derive properties such as temperature and density. And this spectrum is typically observed in the near infrared. So we can observe this spectrum, for example, from ground-based telescopes, but also from the James Webb Space Telescope. What do we know about Uranus ionosphere and its aurora, though? We know very little, first of all. There were some flybys, well, one flyby from Voyager 2, which resulted in the discovery of ultraviolet aurora. The aurora in the ultraviolet resulted to be quite patchy, but also very localized. Very, very few models were derived from this limited data set from Voyager. And here I'm showing one of the vertical profiles derived from a 1D model that was produced from these observations. As I mentioned, we can also observe H3+ from the ground. This is the first detection and confirmation of the aurora from in the near infrared, so observing H3+ from the Keck telescope on Mauna Kea. Aurora were confirmed by H3+ enhancements in total emission and a corresponding column density enhancement, which allowed to confirm the aurora in the south in this case. Still from this study, the temperature resulted quite limited, the temperature variation of H3+. Nonetheless, the aurora was confirmed with the total density. We have confirmed that we know very little about the ionosphere of Uranus. We have HST in the ultraviolet that observes some auroral emissions and limited data from the ground. But what this data can tell us is the global information of the ionosphere. And what we know about the upper atmosphere, the ionosphere, is that since 1992, observations have reported that the ionosphere at Uranus has been cooling. So what is causing this? We don't quite know, but what we do know is that we need more observations. Therefore, as I mentioned, we have JWST that now observes in the infrared and particularly in the near infrared. NIRSpec on board the JWST has observed Uranus in 2023 across 3 longitude sectors. And here we have the results from Melin 2025. We have maps of total emission on the left, on the center, the column density, and on the right, the H2 plus temperature. We can see from the total emission and column densities that there are localized enhancement in total emission that result in some localized enhancement in density. In temperature, there isn't much temperature variation. Some localized enhancements, but very limited. Another interesting thing we note, though, is this at the center of the total emission map, we can see some darkenings, which also can be seen in the column density map. Now, this was mapped to be the magnetic equator. So perhaps this is a result of the magnetic field topology impacting the ionosphere. There was only another observation on Uranus with JWST, mainly with NIRCam. So this is a near infrared observation, but only in camera. So it does not give us the spectrum. This mapped once again Uranus across 3 longitudes, and what resulted from it, what we can see here in the map on the right, above the limb, there were enhancements just above 1,000 or 2,000 kilometers. Once again, as I mentioned, this was a camera. So whilst we can see enhancements, we can't measure temperature or density of ions. So what we needed were observations with NIRCam. So JWST Programme 5073 was conducted just over a year ago today, in January 2025, and observed Uranus for the first time for a whole rotation. Now, this cannot be done from the ground because a whole rotation is just over 17 hours. Whilst here we can get all of the spatial information of the planet. We can see even just from this GIF, different dynamical structures and also distinct auroral features. However, on this talk today, I am focusing on measurements above the limb. So here we can see that there's the planet at the center, and what I focus on is everything above the planet, so above the limb. We use the methodology used on Jupiter dataset in Tiranti 2025 that used the Tikhonov regularization to invert the spectra along the line of sight to obtain local parameters for the spectrum. What this means is that it allows us to derive properties locally and vertically, so at different altitudes in the ionosphere. So we clean the spectra using an H3 plus open source fitting tool, which is happy. And I bin the spectra every 350 kilometers altitude. Here I'm showing a spectral fit at the middle, at the ionospheric peak, at around just above 1,000 kilometers, and then just above 3,000 kilometers. And we can see that there is quite a clear fit. There is very little impact from other molecules, such as CH4 at Uranus, since the ionosphere is quite extended at Uranus. So from the spectrum, as I mentioned, we can derive the physical parameters such as temperature and volumetric density. Here I'm presenting the global profile. We can see from the map below the points that the observation covered. As I mentioned, these observations were carried for a whole rotation, so we have a full longitudinal coverage. However, because of the tilt of Uranus, it doesn't cover all latitudes, but mainly latitudes between 25 north and 25 south. So from these vertical profiles, these global vertical profiles, we can see temperatures peak above 3,000 and 4,000 kilometers altitude, and the density peaks just above the ionospheric peak, which is above 1,000 kilometers. What the temperature tell us when we column weighted them is that temperatures are around 426 Kelvin. Now, this confirms the long-term cooling at Uranus that I mentioned before. Although temperatures column averaged are slightly higher than JWST temperatures reported from observations from 2023. And this is because, as I mentioned, these observations are above the limb. So they focus on the terminator. So it could be that temperatures are slightly enhanced. Now, the cooling trend, as I mentioned, is still being investigated. It has been attributed, for example, to the solar wind power, but this is still debated. So we can map these parameters also in longitude, since we have a full longitudinal coverage. I map parameters every 80 degrees longitude, and here I'm showing the temperature map across longitude, and then different altitudinal sector in the histogram below, still across longitude per different altitudes ranges. Once again, we see these enhancements quite high up in the ionosphere, but this is the base of the exobase. And this was observed, this temperature enhancement at the base of the exobase was observed also with Voyager 2 in the ultraviolet, and with recent analysis of occultation, whether stellar occultations in the visible or with Lyman alpha analysis. What we can see from this map that I'm showing, both the top and the bottom, is that the temperature variation is quite limited. So yes, there is an enhancement in altitude, but across longitudes, it's very limited, between 50 and 60 Kelvin, which was observed both by JWST, which I've shown before, and from the ground-based maps from Keck that I've showed at the beginning. And this is quite a contrast with the Jupiter and Saturn, because we're used to see very steep gradients at these planets from pole to pole. But this is not the case at Uranus. Emission here, I'm showing the map as before and the histogram as before. And we can see two broad enhancements in the total emission map and in the histogram. But also what we can see in the histogram is that between 190 and 240 west, we see a depletion in emission. And this depletion is also seen when we map the density. So we see the ionospheric peak in this map in density, as I mentioned before, just above 1,000 kilometers and below 2,000 kilometers. The magnitude of the density is slightly higher than what I showed the model from the late 80s from before. And as I mentioned, we see a depletion in density still between 190 and 240 west. And this could be something similar seen in the JWST maps that I've shown before, but also similar phenomena. So a depletion in total emission and a depletion in density has been seen in Jupiter's known auroral ionosphere, as reported by Stallard and Knowles in 2025. Finally, because we have a complete longitude coverage, we can also map the ionosphere per different regions. Here, we've mapped it for auroral regions, so longitudes where we would expect the aurora to be, and non-auroral regions. And then also I've isolated the profile where we saw the depletion in density and in total emission. What we can see from these profiles mainly is that, once again, the temperature, even separating auroral and non-auroral profile, is very limited. The temperature variation is very limited. And similarly, density does not vary much across longitude, apart from the emission depletion vertical profile that shows a peak 25% lower than the median of everything else. Now, as I mentioned before, this could be conjugate to the magnetic equator. And lastly, we can compare this information that we have of the vertical ionosphere with the very few models available. Here, I'm comparing it with the model from MORE 2019, which is a 1D model and one of the few available. Here, this is a vertical profile in the non-auroral region and in the south to have a comparison with the paper and the model from 2019. We can see both in temperature is lower, but as expected, because of the cooling trend observed at Uranus. The temperature profile used here was still from the Voyager observations. And density too is 1 order of magnitude lower compared to the profile at noon, but also at dusk and dawn. This is potentially correlated to the geometry and also cooler temperatures, which therefore impact not only the temperature itself, but also the density. Still the uncertainty that is around the vibrational level of H2 and therefore impacts the ionospheric models, and also just the assumption of vertical field lines in the magnetic model used in MORE 2019. So we need more accurate models since this is a 1D model, but also an updated model with the current geometry and the current temperatures observed nowadays. So to conclude, we have derived the first vertical profiles with global coverage in longitude. We confirmed the long cooling trends, and the vertical densities derived are 1 or 2 orders of magnitude less than models. We note weak longitudinal variation, which could imply that the energy redistribution is quite efficient across the globe at Uranus, but further investigations are needed. And finally, these observations will help constrain not only models, but also models that will be useful for future missions, for example, the UOP at Uranus. Further vertical variability observations and studies will be conducted since right now observations are being carried out with JWST still at Uranus. So we'll be able to compare the vertical profiles across time too. And finally, this paper is under review right now with GRL. Thank you very much.